Thank you, Ganapati. After hearing three very intense SMR talks, it makes my job a little simpler. I will not be talking about basics of SMR or this explaining about fossil fuels and renewable nuclear energy, etc. These are now basics for everybody. Now I will start from the explanation of old nuclear and new nuclear. Old nuclear means big, large reactors, high powers, something similar to mainframe computers. And nowadays we are talking about new nuclear, that essentially means like PC type of things, smaller systems, more reliable, more compact, and basically we are trying to talk about molten salt for simple fuel structure type of systems. So these talks, three talks have explained lots of things on that part. And here we are talking about high temperatures. Simple concept, BSCE concept, this we call it. This is a micro modular reactor. But in the previous talks, you have heard that neutrons have been provided by fission, only fission, coming from uranium or any other fuel, if at all. I'm going to talk about neutrons not generated from fission to start with. Neutrons can be generated by accelerators. Neutrons can be produced in laboratory using proton accelerators and electron accelerators. And I'm talking about neutrons generated from accelerators. This concept of heat removal from the molten salt, etc., I will not touch upon. I'll only talk that electron beam can produce neutrons, and number of neutrons can be controlled by the amount of electron current we introduce in the reactor. So that essentially means beam power, reactor power can be controlled only by controlling electron beam current. So that makes it more safe. Safe in the sense, reactor cannot become overcritical. Whenever there is a chance of power increasing, we can control beam current, which is an input parameter from the accelerator. Here, there are two ways. Electrons can be generated using protons. Protons means by spallation process, or they can be generated using electrons, but there is a big difference between the two. Proton accelerators are more efficient in neutron generation, neutron production. For example, a 1 GeV proton can produce about 20 neutrons, whereas a 60 MeV electron can produce only 0.02 neutrons. So currently, there are some projects running in the world where subcritical reactors operation using protons is being followed up. There, this is a Mar' reactor in Belgium, which is a 600 MeV proton, and you can see this is about 400 meters long. And it is a good project which is going to be commissioned in the coming 5-7 years. I'm not exactly sure. It is in advanced stages, and it is going to give lot of data for accelerator-driven subcritical systems. as an alternative, we propose a electron accelerator generated neutrons, which can be a good alternative to proton beams. Electron accelerator, you can see the second part. This is a 40 MeV, 120 kilowatt electron beam system, which is commercially available and is used for medical radioisotope production. So we propose to use this kind of accelerator for adoption in SMR systems. You can see the size of this thing. This accelerator is hardly 3 meter by 3 meter by 3 meter. So much smaller than this conference room itself. Coming back to the basic process of neutron generation. We have electron beam particles, and then it impinges on the fuel, that is U-233, and the thorium or U-233, and then that produces neutrons. And these neutrons are produced in two steps. One is it produces X-rays, and X-rays are used to produce neutrons. These neutrons then follow a fuel cycle similar to SMR, and they produce further neutrons. So as we know, we operate reactors in subcritical mode. In case of protons, to produce 100 times, you need 0.94 criticality. And for electrons in a single cycle, we need 0.999. Of course, this is for single cycle. Whereas in a coupled cold reactor, where we can use two cores, first core is a fast kind of reactor, where one neutron can be producing one neutron, and remaining can go in the second core, and they produce 10 neutrons. So a gain of 100 can be generated in this. Estimations have given in a single core reactor, if we have a 0.99 criticality, we can go for a power production multiplication of about 100 in a single core reactor. Whereas the same 100 multiplication we can get using a dual core, where fast and thermal, both kind of reactors are in operation. We can get a gain of 100. That gain of 100 means a lot. You use 100 kilowatt beam and you can get 10 megawatt beam, so 10 megawatt power. So 100 kilowatt beam is very, very easy to get in electron beam accelerators. A alternate design for dual core reactor I have shown here. The bottom figure, if we see, the dimensions are very small. It is about 3 meter by 3 meter. I will not go in the depth of this design because this is coming from simulations. One can see the dimensions only. This is too compact, and so far it looks good. Simulation studies are in progress. More details are to be worked out. And two kinds of reactors, 10 megawatt and 300 megawatt architectures are being worked out. And fission products build up, protactinium depletion, etc. have been studied. And it is felt that these are workable solutions. In the near future, these things will be practical. And I now give a summary. and current status. Electron accelerators currently are easily available, commercially available up to 100 kilowatt level. In India itself, in industry, today at least 40 to 50 electron accelerators are working for various radiation processing applications. And up to 500 kilowatt electron accelerators are commercially available. IBA 40 MeV 120 kilowatt beam can be used for neutron generation and coupling to a SMR core. Electron-based ADSRs are very compact, and in case of a coupled core system, a gain of 100 is easily possible using electron accelerators. Gain of 100 means that you need hardly about 100 kilowatt to 200 kilowatt beam to get a power station of 10 megawatts. And criticality is not a problem. It will always be operated below criticality level, so no accidents are forecasted because it will never go critical. So my suggestion is that BSCE micro reactor with 40 MeV, 120 kilowatt accelerator using should be taken up at the earliest so that neutrons produced in the first stage can be used for medical applications, and after some time these neutrons can be injected into a SMR core designed and developed as per the earlier calculations, can produce electric power, thermal power for industrial applications. I just suggested to Dr. Timothy, sitting here, instead of this fission neutrons, we can introduce neutrons from the accelerator in their design so that progress can be faster. For power generation, you basically need neutrons. Their source can be fission, or it can be accelerators. So neutron generation in accelerator is a very well studied out area. Can be generated with highly reliable way. So if we can introduce neutrons generated from accelerator, electron accelerator, into a core of their Texas accelerator, maybe we can do much faster work in this area. Thank you.
Thank you, Kailash.
Any questions? Okay, thank you.
All right, next is our good friend who traveled from Tokyo to Geneva. Dr. Professor Akira Yamamoto is going to give us next presentation.
Okay, can you hear me? Can you hear me?
Yes. We can hear you, Akira. Go ahead.
Can you hear me?
Yeah.
Can you hear me? Hello?
We can hear you.
Can you hear me? Can you hear me? Hello?
We can hear you, Akira. Looks like maybe you're not hearing us. Show thumbs up.
I'm trying to use my. Okay, in that case, fine. Can you hear me? Can you hear me? Hello? Can you hear me?
Bara, just show thumbs up. Yeah, I think he cannot hear us, looks like.
Sir, can you hear us?
Yeah, I can hear you.
Yes, sir. I'm sharing your presentation.
Okay. Please. Okay, thank you very much. And so my presentation will be quite similar or more practical example for the electron superconducting RF accelerator technology can be applied for isotope production and also future electricity production as well. So thank you very much for this opportunity. So next slide, please. Next slide, please. Okay, so I tried to make an introduction how the electron superconducting RF accelerator has been developed, and one of the example at KK, we are trying to develop the so-called compact electron recovery line accelerator, and that's try to be used for the isotope production. That's I try to explain. Then these are kind of SRF line application, and future how we may expect the superconducting RF technology can be more advanced. That's summary. Okay, next please. Next slide, please. Okay, these are just a history of the particle accelerator, and since 1970. The most of large particle accelerator system becomes a superconductivity application. Of course, one is a superconducting magnet for the hadron accelerator, proton accelerator, the lead squared part, and now the advanced hadron accelerator LHC is now functioning so well. There's a blue line, blue dotted is a electron RF accelerated, sometimes ring accelerator and sometimes linear accelerators. And next slide, please. And as you know, the superconductivity, we may need to have a special materials, niobium, titanium, or in these days, we are trying to go the niobium-3 tin to make more powerful RF power and also magnetic field as well. So next slide, please. And the feature of superconducting RF is a so-called high Q, is the resonance efficiency is quite high, with a very, very low loss of the cavity. When most of the power put into the cavity can be transferred to the beams without the losing of the Joule heating of the cavity itself. That is very important. Then it's so-called high Q. And low frequency, because of this very low, low loss, we can make a large aperture of the cavity that can be useful for the high-intensity beam accelerators. That is really important for the energy production and also isotope production as well. So, of course, we have to have a kind of drawback, cryogenic required. So, that's why so it's high Q is so important. Next slide, please. So in these days, those horizontal axis electrical gradient, electrical field gradient, and the vertical axis Q value, resonance efficiency. And in these days, compare with a normal conducting cavity, so more than 1,000 or 10,000 higher the Q value can be expected. And even superconductivity now is more, one order magnitudes are getting improved according to the surface treatment improvement. Okay, that is the technology. And the upper part is a superconducting cavity and made of niobium, titanium, niobium, pure niobium, and the lower one is copper-based normal conducting RF. Because of the, as I said, the Joule heating and the normal conducting cavity have to be very small and small aperture. And the superconducting cavity can have a large aperture. It means it can carry more the beam without disturbing a higher order of the loss as well. So next slide, please. And this is a kind of, in these days, superconducting RF accelerator, and one of the most recent, very successful facility is so-called European XFL project, and about 1 kilometer long superconducting RF cavity, then accelerator, and about 800 cavity are installed and perfectly working. And now, the right-hand side, LCLS2 high energy is an American case in the Stanford Linear Accelerator Laboratory in collaboration with Fermilab and Jefferson Lab. They also developed successfully a similar accelerator. And in China, also the yearly comings, the so-called SHINE project, and coming realized. And in Europe, ESS, European Spallation Source, in this case is Proton, accelerator is being built, and it will be completed soon. And at KK, so as aiming for realizing international linear collider, we are collaborating with other laboratories around the world. And it's once we developed a superconducting lineup, S1 Global, and it becomes so-called superconductors facility recently. And also, I tried to introduce a compact ERL system. It's very unique and very efficient electron accelerator systems. Okay, please, next slide, please. Okay, next, please. Okay, this is about 10 years ago, the KK developed compact means still a smaller size, but in future it can be enlarged depending on the application. In the center of the super KK electron and positron ring collider. So we developed a compact ERL system. And so right-hand side is a figure photo shows inside of compact ERL. And the top part is showing the electrical cavity systems developed at KK. So next slide, please. Okay, so that's again showing, so center of KK, center location KK, we have this electron compact energy recovery line system. And I try to show next page, it's a kind of principle. Please, next page, please. Okay. So this is a electron energy recovery line system. And once electron is accelerated, and it may have energy, and then next after one time coming back, and this energy can be used for the new the electron would be accelerated. But today's presentation is not the main purpose of this electron lineup, but by using this existing the electron superconducting line accelerator, we try to use the production of the molybdenum isotope production. So the bottom part, left-hand side, green, so it's an injector, and the blue one is accelerated. Then it can be extracted to the production of the isotope. So please, next slide, please. So this is more like a schematic view of the energy lineup. So the left-hand side, so you can see the gun, the left bottom part, left bottom part is the injector, and it's getting to the main lineup system, and it will be extracted to the so-called irradiation beam line with CW mode. Oh, what's happened? Okay, so anyway, yeah, oh, thank you. So by using the few 10 million electron volts, the electron is extracted, and then it will be hit the converter, and it can produce the molybdenum 100 molybdenum target 100, and it becomes the molybdenum isotope 99. This is successfully tested, and it can be a good example for the electron lineup can be very practically useful for this kind of application. Okay, next slide, please. So, and then a kind of electron beam can be used also, this as an idea already explained by previous speakers. So we can use this electron beam into the thorium reactors, and it can create neutron, and then it can be used for the energy production and applications. This are kind of next page, please. Yes, this was also the idea was proposed by Japanese scientists already much before, and of course at that time it's proton, but we can use this kind of principle by using electron lineup. Okay, next page, please. And as it was explained, so of course efficiency of the neutron production would be lower in electron case compared to proton, but it can be quite cleaner, and also the less radiation protection shield, so on, and the system becomes a much simpler and easier to be realized, and the cost-effective way to be realized. And okay, next page, please. And so, as also explained, so this kind of system is now proposed by the BSCE, and we can expect this can be realized in our future. Okay, next page, please. And if you look at the progress of the SRF accelerator technology and performance, so it's kind of started this kind of history is 1990, and now we are here is about 2020, 2030, and the gradient of the cavity becomes more than 7 times becomes higher. So this is a great progress realized. It means we can expect future more the compact electron lineup, superconducting lineup with much better energy efficiency for accelerator itself. And one of the most important demonstration was done in European XFL. Now it's the 800 cavity produced, and more than half of about 30 megavolt per meter has been achieved. Is a kind of more than 50% of cavities. And, okay, so future maybe we should look at more higher gradient. And yes, please next slide, please. And so of course by optimization of the cavity shape and the field itself, and also surface treatment, and also the how to use the electrical field. In case of standing wave, we can use not a peak field gradient, but if you use traveling wave. So traveling waves mode can just almost a kind of we can use a peak electrical gradient. In that case, we can expect much higher effective as electrical gradient, electrical field gradient. And that is a kind of way for improving the technology for SRF accelerator. And also, if you look at another material instead of niobium, if you can use niobium-3 as basically the critical temperature and critical V is much higher. In this way, we can expect a kind of doubling of the order of doubling the field gradient in some futures. And of course, if you can invent a new way of cavity fabrication, so cost-effective cavity production can be expected. And that this effort is also being carried out. So that is a kind of future we can expect. So please, next slide, please. And summary. And the SRF technology is a key technology for particle accelerators and the various applications. And especially for the KK, compact ERL facility, contributing to demonstrate or investigate SR accelerator technology application, in particular for medical isotope production, such as module 99, critically important. And also, this technology can be extended as a cleaner and economical approach for thorium-based energy creation, taking great advantage of natural availability, especially in India. And of course, to realize more this kind of technology to be practically applied, a global R&D cooperation effort is very, very important. And now a possible international cooperation between KK and Indian institutes is anticipated and under discussions. Okay, that is my presentation. Thank you very much for listening. That's all.
Thank you, Akira. Are there any questions for Akira, please? No? Okay, we move on. Thank you very much.
Thank you very much.
Next is Manoj. Please. Yeah.
Thank you, sir. So I don't have any presentation. Now I will be only discussing about India's plan for the nuclear expansion. After Fukushima, nuclear has taken a center stage worldwide and India also. We have committed our net zero goals by 2070. And as per our modeling requirement, we see that 100 gigawatt of nuclear energy by 2047 as a one roadmap to achieve this goal. And we see that even after the 100% electrification of the hard-to-abate sector and the other sector, there are the hard-to-abate sector processes which cannot be rectified through the simple means of renewables and other things. So the nuclear may be one option for us. And for that, we are planning 100 gigawatt, and we are basically seeing that how we can expand this, the existing 8 gigawatt to 100 gigawatt. Currently, we have 8.2 gigawatt of nuclear energy, and around 15 gigawatt is under construction. And if we want to achieve 100 gigawatt, then definitely we require at least 4 to 5 gigawatt per year from now onwards. And for that, recently in our budget, there is two announcements. One announcement is about the 100 gigawatt through private sector participation, and other is about the 20,000 crore rupees, a mission mode approach for the SMR. So the SMR is a part of the entire nuclear journey. It's not the only SMR that we are attempting. We are attempting both the larger plants and the SMR also. But till now, we have restrictions for the private sector under Atomic Energy Act 1962. So only government or government-owned company can establish the nuclear power plant and own nuclear power plant. So right now only NPCIL is establishing the entire nuclear fleet, and only recently the NTPC and NPCIL joined hand and they started doing the Aswani project. So for that, lot of changes required if we wanted to achieve 100 gigawatt. And these changes are especially the regulatory and policy changes that we are attempting. And in that regulatory and policy changes, the major changes basically is start with the Atomic Energy Act 1962, and obviously the Civil Nuclear Liability Bill, which is a major hurdle for having a bilateral or G2G or B2G business in the nuclear energy nuclear energy technology collaboration. And after that, ARB, Atomic Energy Regulatory Board, which is a licensing body for the nuclear project. So this also requires statutory clearances, status, and also requires strengthening, because right now it's working under one administrative setup. Then after that, once we have the huge nuclear power plant, then we require a dismantling authority, because right now to operate nuclear power plant in India, the skill is limited, and also the dismantling skill is also limited. So two agencies, which is one is that National Radioactivity Waste Management Agency, and other is about the dismantling agency. This is required to be established. And then obviously the new designs for that SMRs and the long-term like generation 4 technologies, especially for the higher temperature and higher pressure technologies. So right now these are the new prospect that is emerging out, and NITI Aayog and Department of Atomic Energy is working together. So we are working together on the Atomic Energy Act, and which is to see that what sections and what paras is required to amend so that the private sector participation can be encouraged. And obviously the civil nuclear liability will where there is a section 17 and some other section which is basically unexplained, or it's basically miscommunicated in the forum. So that is also attempted to see that how we can expand and how we can change this thing. So along with the Atomic Energy Act, a lot of other things are required to change. So especially if the private sector is coming, so they require safety, security, and safeguard issues. So safety, security, safeguard issues are a major challenge. So how to basically handle the fuel. So whether they can go for the enrichment of the fuel, or they can utilize the waste of the fuel. So these are the new concern which is emerging out, and this is required to be taken care through the policy and regulatory things. And also that once private sector is, if suppose that if they are leaving the site without completing it or without, there is some incident happen, then what will happen after that one? So a lot of insurance things are required to be covered up, so that who will take over after that. So these are all under discussion at a different forum, and I hope that Atomic Energy Act will basically cover all those ambit which require to promote safety, security, and safeguard, and especially for the private sector participation. Coming on the special focus on the SMR, so NITI Aayog and Department of Atomic Energy, we publish role of SMR for nuclear for energy transition during G20 in India's presidency, and it's almost 2 years back. And after that, we have taken several initiatives for the SMR things. And right now, Department of Atomic Energy and BRC, they are now developing the new indigenous design. And under this announcement of 4 to 5 SMR by 2030 under the budget, so they started developing their own design. So currently, we have PSWR design, which is now indigenized design. However, we see that worldwide 80 to 90 designs basically depend upon the LWR design. So DAE and BRC also opting a lot of new combination, that whether to focus only at PSWR design or LWR design. So they are doing the design part, and after that they have a plan for site selection and all those things. Now NITI is supporting them to even to connect to the different foreign companies. So we had a discussion with the Westinghouse, we had discussion with the Rosatom, we had discussion with the Holtec, and we have understood that how they have, what advancement they have achieved in their design and development. So right now, Rosatom and Holtec, they are in the advanced stage, and they have committed timelines for establishment of their first plant, and a lot of other foreign companies. And we have a discussion, we have completed the first round of discussion. Though there's a lot of other challenges, like with the US 810 and 110 is a challenge that how to go for the technology transfer and technology collaboration. Even with the Russia, to a discussion at a G2G level is required. So these are the new things that now NITI Aayog and Department of Atomic Energy, we are collaborating with them. NTPC, which is right now starting the new nuclear wing. So definitely we require more such PSUs to come forward to join hand with the NPCIL and to establish the SMR and other things. So these are the new developments, and NITI Aayog and DI is working together to achieve, to prepare a roadmap to achieve the 100 gigawatt of nuclear energy. Thank you. If you have any question, I can answer.
Just a quick question, Manoj. So you're saying that the nuclear bill is being debated now, which means you're incorporating some concepts. You mentioned public-private partnerships. Are there going to be enough alternative ownership structures for negotiating external capital to come in? Otherwise, you're not going to have enough money.
So right now, yes. So right now, the Atomic Energy Act is a major regulations for having new companies. So this is under process for amendment. So under that, they are trying to open the entire sector. So we have a Company Act. So company established under Company Act may be one option. So any company, private or public. Now, for considering that capital inflow is in form of FDI and FFI, obviously that today nuclear is restricted for any investment because Act is also not allowing, and also there is no atmosphere for that one. But yes, there is a time to see that whether we can open this sector for FDI and FFI, but it is not done yet, and it is under discussion. However, if we wanted to achieve 100 gigawatt, definitely we require a lot of capital. And we require a lot of collaboration. So thinking this 100 gigawatt roadmap, definitely the plans are to open this sector. But how and when, it is under discussion. Good. Thank you very much. Thank you. Yeah, please.
Seems interesting, especially because it's 12.5 times more than what we are having in the capacity. But considering the energy consumption in 2047, that would be lesser, and I think our energy consumption and the nuclear's contribution in the energy consumption would be lesser than that. So what's ultimate plan for the government after 2047? And considering the capital allotment in the national budget for the nuclear energy mission, is it also accounting for the pink hydrogen economy, or it's only accounting for the infrastructure development for the new reactors?
No, if you see that we have a commitment, and if you see the entire roadmap for net zero, so anyhow, right now we have a 210 to 265 gigawatt of coal, and anyhow, as per modeling scenario, that coal fleet is going to saturate by 2047, something like 2040, something like that. So what are the alternative for that coal-based power power, because we are a huge country and we have a national grid. So for us, the base power is more important. So today, if you see that there is 2 to 3% of nuclear energy contribution in entire energy mix. So for that, if we wanted to reduce coal, so we have to have some new fuel so that it can balance the base load. So this is what one thinking, that if we wanted to invest from today, and then if there is a coal decline, then this nuclear can pick up and balance out the base load. So the first thing is that to balance the base load. Second thing, obviously, that we wanted a clean energy, so the nuclear is one of the cleanest forms of the energy. Now coming on the green hydrogen, so right now in Gen 4 technology, especially the SMR, you can directly produce the green hydrogen through SMR. So you don't require to again go for electrolyzer things. So that's why I'm saying this, the technological development, like we have heard a lot of new technological development, especially on the molten salt reactor, something like that. So this new technological options, which basically Gen 4 technology, which is not started in India also. So if we focus on that one, the green hydrogen production can be done through the SMR. Yes, the infrastructure which is required to build massive 100 gigawatt is still missing. So for that, site selection, proper planning, and also the manufacturing and supply chain management. Because for the 100 gigawatt today, if you see that if you wanted to 4 to 5 gigawatt per year, for that you require to have at least maximum supply indigenous, because you cannot depend on the outside. So these are all the infrastructure issues. That's why the government is basically pushing this sector, and they have taken this initiative under the budget. Yeah. Thank you, sir.
So just a question.
So next speaker is Thierry.
Thank you.
So good morning, everybody. So I was a little bit frozen here, so I tried to warm up a bit more. So let me give you a brief overview of the strategy approach in France to push forward SMR on AMR. 2 years ago, the French government has engaged 1 billion euros with a clear goal is to start the building of a first light water SMR in France, and also another prototype of so-called another technology. It has also been considered that the nuclear industry is no longer dependent solely on R&D and public funding. And so the reason why it has been adopted an entrepreneurial mindset to increase the dynamic to push the SMR on AMR new ideas. So startups is the basement of this approach. 11 startups have been supported by this 1 billion euros project in France. But it's also combined with the needs to attract private investments. This is the rule for these 11 startups. It's also considered that SMR is not a technology, it's an industrial and economical strategy to compensate what we call the scale effect with conventional nuclear power plants, with the idea to have serial production, prefabrication, simplified design, and new markets beyond power to the grid. This is for all of us the fundamental idea. However, it has also been considered that the startups still have to rely on a solid scientific foundation, and also to be based on knowledge and expertise of highly qualified engineers and researchers from what we call the historical majors. And just to remind you, in France, we have the French Atomic Energy Commission, the EDF, major utility, which is again a state company, but 2 years ago it was a private company. So the reason why in UK they got the market to operate all the nuclear fleet, historical fleet in UK. Also Orano, who is the, as you know, producing of uranium and enrichment facilities. Andra, which is the company in charge of final disposal in France of nuclear waste. And of course, the French Nuclear Safety Authority is also engaged in this approach. We will talk a little bit about this point later. Another key point, which is also integrated in the strategy, is to keep into account the closing fuel cycle for this new SMR and AMR. It's the case for what we call the Gen 3 and Gen 4 as well SMR technology. So here is a general picture of the SMR AMR projects currently developed in France. There are 5 types of technology. You see that at the top of the picture. So fast lead reactors, 2 light water reactors, high temperature reactors, molten salt reactors, and fast sodium reactors. And on the y-axis, you have the power scale of each of these examples. So Nucleo is fast lead reactor. So at the moment, it's probably one of the 2 major startups with a high amount of manpower. There are about 100 people in France working in this project. So yes, another important information, you see the purple color, this is the electricity power scale output. On the red color is the heat power to be produced with these reactors. So for light water reactor, it's a small power project. I will show you in a moment more details on this one. For high temperature reactors, this is the blue capsule, which is supported by the French Atomic Energy Commission. We have also the Jimmy, which is only, the project is to produce heat, only heat. The other one with molten salt reactors is Stellaria. Stellaria, with the objective to produce electricity and heat. Another one is Thorium. Again, it's to produce electricity and heat. Narea, again, with a lower power output, but electricity and heat also to be produced. For the fast breeder reactors with sodium cooling, there is the Hexana project and also Otrera project. So let's show me into more details. What are these projects? So I will start first with the new one, which is a project developed by the EDF utility. So it's a Gen 3 plus pressurized water reactor technology, fueled with UOX fuel enriched. It's a classical fuel. It's capable of producing electricity from 300 to 500 megawatt, and also heat up to about 100 megawatts, but in a cogeneration mode, of course. The design is based on proven technology bricks only. No innovation to be taken into account in this project. Why? The idea is to be in time for the market. This is the goal. It's a modular approach on off-the-shelf components, of course. The construction is to be done in 48 months, not more. So at this stage, we are in the, EDF is working on a conceptual design, and there is still time to co-develop with other partners until the basic design, which is scheduled after 2026. So the other case of light water reactor is the Calogena one. It's a Gen 3 pool-type research reactors. The advantage is that it will work at low pressure, not more than 5 bars, but with conventional UOX fuels. It will mainly be used to produce heat in order to decarbonize district heating. And 2 days ago, it has been decided by the French government to install this project in a nuclear research center in south of France, in Cadarache, to heat the center. So this will be the first prototype to be installed there. Some other study case. These are the examples for fast breeder reactors. So the first one is a sodium cooled fast breeder reactor called Otrera. So the interest of this one is that it's a reactor in ground. So this will need less than 1 hectare of ground to be disposed. It's a cogeneration project, electricity on thermal. It will use MOX fuel, plutonium-uranium fuel, for up to 10 years of duration without any refueling. 4 containment barriers, so highly safe projects. And this project will not need a test reactor. The first in kind will be built directly. Another one interest is the Hexana project. It's 2 modules, 400 megawatt thermal reactors combined. And the idea is to have a disposition to store the heat. So the idea is to produce without any modulation the heat, to store it in an intermediate facility, and to deliver it as a function of the needs for the market. Another one which is developed is the lead fast breeder reactor, lead cooled fast breeder reactor. So it will be first based on a test reactor of 3 or 30 megawatt electricity. The land acquisition is done. It's in a nuclear power plant in France. It's a Chinon site. It's already in cooperation with other countries, ENEC in UAE, Sweden, and also with Saipem, which is a petroleum company, Italian petroleum company. And also the generic design was assessment was requested in UK. So this is one of the opportunity to work with other countries already. So the question for this today meeting was to answer some questions. So we tried just to put some answers according to the current development we are doing in France. So first, SMR need to be licensed in several countries in order to establish a series. So the need to join efforts required from regulators. This is what we have done with the NEWARD project in Europe, with 6 safety authorities involved already in the discussion on this design. We have also considered that it's very important to start the licensing processes as soon as possible, even with a pre-concept design. This was not the historical approach in France. The French safety authority has always waited to have the final design available to start its study and to give the next step, which is, of course, the licensing. So this is a change in mind, even in our safety authority. Very important from our point of view. It helps the engineers to improve the concept. Third, fuel types depend on the reactor technology. And of course, there are different readiness levels and also technology and product production capacities have to be considered. So, industrial fuel fabrication facilities exist, in fact, mainly for light water type reactors at the industrial scale. So what about the current technology? I would think the light water reactors. Of course, the positive points are industrial fuel supply chain available, extensive feedback on safety and component fabrication. But there is a limited range of heat supply in terms of temperature, which is close to 200 degrees Celsius max. So it will not give the solution for all the off-grid needs. And here again, the expected time to market for the first units, if we consider the European market, is 2030, 2035. What about the more innovative design, which are Gen 4 reactors or advanced modular reactors? Of course, higher temperature heat available up to 800 degrees Celsius. This is the main advantage. A better use of plutonium, nuclear materials, for most cases. We have plutonium. We have stockpiles, in fact. If we consider all the UOX spent fuel already stored in the pools all around the world. However, the technological readiness level needs to be improved for some designs. And more or less feedbacks from existing units with perspective of licensing has to be improved. And of course, the industrial fuel supply chain availability is a question. And according again from the European market, the expected time to market for the first units will still need 10 years, 15 years. So these are the main information I wanted to share with you today. So, thanks.
Any questions from the audience? If not, so thank you very much again. Chandra, please.
Hello? Thank you. I am CP Tiwari from Tata Power. So, today in 2024-25, we are talking of clean energy and CO2 free energy. But our founder thought of clean energy 100 years back, when we first established first hydropower plant in India, way back in 1955, we commissioned first hydropower plant in the state of Maharashtra. And message was clean, cheap and abundant power is one of the basic ingredient of the economic progress of city, state and country. And as such, Tata Power have been the lead adopter of technology in power sector. We have been the first one who has established 150 megawatt unit, 150 megawatt thermal unit, 500 megawatt thermal unit, and then in the field of renewable also. In terms of capacity, we have a total capacity of 25.6 gigawatt, out of which around 10 gigawatt is under construction and 16.8 gigawatt is clean and green energy and 8.9 gigawatt is thermal energy. We are also there into the transmission and distribution, and we have an operational transmission asset of 4,633 circuit kilometer, and under construction asset is 2,414 circuit kilometer. We are also distributing electricity in 4 states, that is Maharashtra, in Mumbai, Delhi, and then Odisha, and then Ajmer, and we are catering to 12.6 million consumer. We are also there in new age energy solution, 4.9 gigawatt we have solar module and cell manufacturing capacity. We have also signed 2.8 gigawatt pump hydro storage project, out of which 1 gigawatt is already under implementation stage. And we also have 5,500 public EV charging point spread across 580 cities in India. So in terms of capacity mix, I already spoke thermal, and we are spread all across the India. We have global footprint also, like we are there in Georgia, we are also there in Zambia and Bhutan, where we are owning and operating hydro asset. Already we talk about budget announcement by Honorable Finance Minister about Bharat Small Reactor, about Bharat Small Modular Reactor, and research and development in SMR, and 20,000 crore budget capital outlay for developing 5 SMR technologies, and then finally amending the Atomic Energy Act and Civil Liability for Nuclear Damage Act. So we are awaiting, we as Tata Power are awaiting for these development so that sector is open for private participation. For the time being, NPCIL has already come out with a RFP, right, in which even without doing amendment into Atomic Energy Act and Civil Liability for Nuclear Damage Act, private players can participate in nuclear power project, and they can develop along with NPCIL nuclear, they are calling it Bharat Small Reactor, which is based on 220 megawatt precise heavy water reactor technology, and they will be offering this technology to private developer. Private developer can finance, build, and then they can finally transfer that asset to NPCIL for doing the operation part, so that when we are transferring that asset to NPCIL, so that whatever civil liability for nuclear damage or whatever Atomic Energy Act is there, as per Atomic Energy Act, only the public sector undertakings can build, own and operate nuclear power plants. So those issues are taken care. And in this model, they have proposed 4 different agreements which is to be executed between users. Suppose any user is there who want clean power for decarbonizing their industrial processes, so they can approach to NPCIL and they can set up these Bharat Small Reactor. So already this RFP is already there into market, and many private players like Tata and many other private companies are already working on this proposal. There are certain challenges in this model also, which is yet to be clarified by NPCIL and Department of Atomic Energy.
Quick question?
Yeah.
Just for clarification.
Yeah.
Can Tata Power play a role in the private player's side to lead international companies participating?
No, actually, in the present Atomic Energy Act, as such, any private player, not only Tata Power.
No, but could Tata Power be one?
So Tata Power cannot work in atomic nuclear power field in India, and we don't have license, okay? And that is why they have come out with a unique model in which NPCIL will be having the license for operating the asset, and Tata Power will be having agreement with NPCIL. We will be doing the investment, we will be building the plant, and after building the plant, we will transfer that asset to NPCIL for operation. Because presently they are only authorized to, they can only have the license for operation of these assets. But having said that, since Atomic Energy Act is being amended, so once that is amended, then private entities like Tata Power can also directly work on these BSR or small modular reactor or nuclear plant. And for that, we are already exploring opportunities and trying to interact with foreign OEMs also. So, whatever this Bharat Small Reactor, what NPCIL is telling, so that is already a well-proven technology in terms, because it is based on pressurized heavy water reactor, and already 24 pressurized heavy water reactors are operating in the country. Their availability is very, very high. Sometimes it is more 100% also. And then you can see there are instances when these 220 megawatt reactor in NPCIL has operated continuously for more than 3 years also, up to say 962 days, 940 days continuously. So these are very, very reliable reactors, though a little old technology rather than what we are talking of Gen 4 or Gen 3 plus reactors, where we are getting better fuel efficiency, better thermal efficiency, but still in terms of reliability and availability, these reactors are highly reliable. So then 100 gigawatt nuclear energy by 2047, what has been announced in recent budget, is it too ambitious or too little? To say that, yes, if you will see the present legal framework, then obviously this 100 gigawatt appears to be too ambitious, and until unless those whatever has been promised that Atomic Energy Act and CLND Act will be modified and amended, until unless those amendments are taken care, so in the present framework this is a little difficult. But having said that, since government is committed for those amendments, so I am sure that country will be able to meet this 100 gigawatt target too. Potential user of nuclear power, we already talked. I represent a power industry which contribute around 40% of total global CO2 emission, more than 40%. So other than doing the decarbonization of hard to abate sector, power industry also need decarbonization. We also need to switch over from coal to cleaner sources of energy, like nuclear or renewable energy. And renewable energy being intermittent in nature, it cannot be used for process industry decarbonization. And our previous speaker also talked about using this nuclear energy for urban development, urban areas, and all those. So these are the cases where this nuclear energy can be used, and new user cases are also emerging, like we talk about data center, AI, and then decarbonizing of steel, cement, fertilizer sector. So there are multiple uses of nuclear power. We also try to see how the cost of nuclear power look like, and how much capacity is to be installed to get 1 megawatt power, what type of capex. I am talking about here whatever capex we are talking, those are with respect to Indian reactor, because if I'll talk about US reactor or French, so their cost may be little different also. So if you see capex wise, nuclear cost is slightly higher than the hydro and coal based power, but in terms of levelized cost of energy, it is very much comparable with hydro and thermal also. Already our previous speaker talked about key economic driver for SMR: simplification, standardization, modularization, and harmonization. Having said that, though we are talking of that with the small modular reactor, we will be able to reduce the cost of reactor per kilowatt or per megawatt cost of reactor, but it is yet to be proven, because earlier we were advocating that as we increase the unit size, cost reduces. Now we are telling that because of reducing the unit size and because of doing the modularization, cost will further reduce, so that is yet to be proven. My next topic is, because NPCIL and DIE has issued the RFP for Bharat Small Reactor. So we as a developer are facing few issues and challenges in the present framework, and that we are trying to discuss with the DAE, NPCIL and other stakeholder to solve it, like fuel security and fuel cost, because you know in the present legal framework, we as a private utility cannot own the fuel, okay. So we are not sure that how NPCIL and Department of Atomic Energy is going to provide the fuel security, and how they are going to give some commitment in terms of fuel cost also for a long-term, say, long-term horizon of, say, 30, 35 or 40 years. Then if I'll talk about heavy water reactor, so in pressurized heavy water reactor, one of the major input is heavy water also, because if I'll talk about 220 megawatt reactor, so it requires around 300 metric ton of heavy water, and its cost is also very high. In addition to initial fill up 300 metric ton, some makeup is also required. So if NPCIL and DA is planning for Bharat Small Reactor to be set up by private entities, then how they are going to expand their heavy water production facilities so that can cater to this requirement. Then our third concern is nuclear waste, because you know we as a private entities would like to put these Bharat Small Reactor for captive generation. So obviously we will be going for a smaller unit like 2 into 220 or 4 into 220. So for those, whatever nuclear waste will be generated, so we are requesting government to make a centralized away from reactor facility, because ultimately these waste are the property of Department of Atomic Energy. So they should develop away from reactor facilities for storing these nuclear waste. Then O&M cost and NPCIL expertise charges, because what is happening that when we are seeing the manpower requirement and O&M cost of these pressurized heavy water reactors, so cost is very high. So we are discussing how we can reduce the cost. Business model is also a concern, because in present business model we have to yet to get some more clarity how that funding will be done. Then availability of skilled manpower, because you know tomorrow if we want to build the plant, from where we will get the engineers, fitters, builders. So they definitely government should also take some action on those things. Supply chain, there are certain critical component, especially if I'll talk about BSR or 220 megawatt pressurized heavy water reactor, there very limited manufacturer are there. So how we are going to augment those supply chain, that is also to be seen. And then one more very important, because when we are talking of a small modular reactor or MMR, so there they are talking of reducing the exclusion zone and avoiding the emergency planning zone. But in the present Bharat Small Reactor or in the present AERB guideline, you have to maintain a emergency planning zone and exclusion zone of 1 kilometer. So finding a site where you can create an emergency planning zone of 15 to 16 kilometer, especially when we are planning to set up these Bharat Small Reactor for captive use. So obviously in captive consumption, I would like to put this Bharat Small Reactor very close to the user point. Suppose I have a steel plant, so I would like to put this reactor very close to a steel plant. Then how I will maintain a 16 kilometer emergency planning zone or 1 kilometer exclusion zone is also a challenge. And that's where we are looking that once these small modular reactors are designed and those are commercialized, so I expect that there will not be any emergency planning zone requirement in those small modular reactor, and those can be fitted in the existing, even in the existing thermal power plant or even within the existing industrial facility also. Then whatever present BSR design in India is there, that is designed for seismic zone 3 or 2. And you know, some of the industrial application may require designing of reactor for zone 4 also or zone 5 also. So we are requesting NPCIL to change their design and make it suitable for seismic zone 4 or 5. Exclusion zone I already talked about, and then finally capital cost of BSR and levelized cost of energy. Because ultimately whatever we say, finally if this electricity has to compete with other sources of electricity available in the country. Okay, if today in the country we are able to generate round the clock renewable energy at the rate of 5 rupees or 6 rupees per unit, and if my nuclear power cost is going to be more than 5 or 6 rupees, then how that will be justified? That is a question mark. And to make these nuclear power or BSR really competitive, we have also requested Government of India to give it as a green power status, because you know in green power initially Government of India has waived up transmission charges, ISTS charges. Suppose I am putting a plant in MP and I am bringing power from MP to Odisha. So at least I need not to pay the ISTS charges. So on that line, because when initially solar and wind power we are developing in the country, so government has provided some incentive so that industry can mature. So on a similar line, developers like Tata Power are requesting to Government of India to consider those type of incentive for nuclear also, for the initial phases, and once the industry matures, then those type of support may not be required. Amendment in Atomic Energy Act, we already talked. In the present stage, private player cannot build, own and operate nuclear power plant, so that change is required. And likewise, amendment in Civil Liability and Nuclear Act is also required, so that foreign OEM can supply a nuclear reactor in India. These are key risks in nuclear power business, and this is overview of different safety barriers what our earlier speaker has also talked of, different zones and exclusion zones and all those. Presently, these are the regulatory and safety consideration for SMR, and India has a mature nuclear ecosystem primarily controlled by government. But we expect that once Atomic Energy Act and CLND Act is amended, then private players like Tata Power will also be encouraged to work on nuclear sector and collaborate with the foreign SMR manufacturer also for setting up SMR in country. That's all. Thank you very much.
Any questions from the audience?
Thank you, sir, for the insightful talk and the mention of RFP by the NPCIL. I found it interesting, but at the same time, I found it a bit ambiguous because according to the 80-page document, the plant load factor of Bharat's small reactor, the 220 megawatt electric reactor, is said to be 68.5%. Which is the actual electrical energy generated over a period of time when the plant is running at the full capacity. But according to the DA document which were released, a few years back, the PLF for 220 megawatt electric reactor is 70 to 80%, and the best performing reactor, Kaiga 1 and 2, is running at the 90% capacity. So how government is looking forward to dealing with the same, and why there is discrepancy between the PLF which is mentioned in RFP and the actual, PLF which is been working with the Department of Atomic Energy. Secondly, because RFP is looking forward to inviting applications till 31st of March. Are other private 31st of April. So are other private individuals being concerned by the ambiguity in RFP, and what impact this ambiguity is looking forward to making on the private sector, which are a bit interested into having the nuclear power station with the utility sector?
Yeah. So definitely we have also raised this issue because, for 220 megawatt reactors, if you see Kaiga 3 and 4 and RAPS 5 and 6, which are the latest units which has been commissioned by NPCIL way back in 2009-10. So there if you see PLF is always more than 90% if you see last 5 years, and sometime it is more than 95% also. So if you are going to do your modeling, financial modeling with 68%, these type of projects are financially not viable. Let me tell you, because we have done a lot of work. And that's why we are asking, because finally in the BSR model, NPCIL has to operate this reactor. So that's why as a private utility, we are asking NPCIL to give, to change their plant load factor to more than 85 or 90%, okay? And that should be the minimum commitment, and then only these type of business models are viable. Number one. What was the second question?
With the given discrepancy, would private industries be looking forward to getting into the nuclear business with NPCIL and trusting them?
Yeah, definitely. So NPCIL has assured us that they will reply to all our concern. And we are still discussing. If they are able to reply to our satisfaction, then only private player will be participating in this BSR program.
Thank you, sir.
Thank you.
Okay, thank you very much.
Good afternoon. I am the last speaker and I am in between you and your lunch. Okay. So I'll not take much time. As quick as possible, I'll finish it. So a lot you have already discussed about NTPC. So I am from NTPC. So I belong to this organization. And for those who do not know NTPC, this is what NTPC is. And primarily it is an energy measure producing 1/4 of India's electricity with about 17% of installed capacity. And we have all forms of energy sources except nuclear. Now we are also planning nuclear. Let us see how far we can go. This is what we are aiming, India is aiming for, not we. So becoming a 30 trillion economy by 2047 and developed country by 2047. Definitely to drive this economy, you need energy, that much of energy, and energy has to come from, of course, cleaner sources. So we are struggling with, you can say, an energy trilemma. That is, one is the clean energy, affordable energy, energy security. All those things are competing with each other. We have to find a solution, the transition. We have to do the energy transition. And as you all know, everybody has realized in the world, nuclear is a viable solution and can provide a possible solution, clean energy source, producing both electricity and energy. This SMR is addition to that, and primarily focusing on energy, not on electricity. So going forward, this is also, I'll not repeat all those things which already been discussed from since the morning. And coming to NTPC, NTPC is in line with the target set by India, that is 100 gigawatt by 2047. How we can meet it? Of course, so in this regard, we are planning all energy, all technology sources, nuclear technology sources, be it PSWR, be it PWR, or the newer technology like SMRs and fast breeder reactors. As of now, we do not have technology. So we are trying to get all those possible technologies which, of course, meets or in line with the Indian program, nuclear program. Much before we started this nuclear business, our corporate plan already includes 2 gigawatt by 2032 from nuclear sources, and we are in the right path to meet all these targets. I'll come just how we are targeting to meet this 2 gigawatt through our joint venture with NPCIL. Already we have a joint venture with Nuclear Power Corporation of India Limited. And we are executing one project that's already been transferred by Government of India to Ashwini, which is a 51-49% subsidiary joint venture between NTPC and NPCIL. There's 4 of 700 megawatt PSWR-based technology is under execution. So we are in the verge of getting the siting clearances. All these studies are already been done. And hopefully within 1 or 2 months, we'll get the environmental clearances also. So by this, we are aiming to meet this 2 gigawatt from nuclear sources. Apart from this, we are also already registered a wholly owned subsidiary company to take it forward further, because as you know, the capacity, whatever you are targeting is huge. So we need multiple technologies, multiple utilities, multiple sources. This subsidiary company was registered on 7th of January this year, and we have already applied to DAE, requested DAE for permission of the board as per Atomic Energy Act. As far as SMR is concerned, I think you asked about 5 SMRs declared by Government of India, whether it is small. The number is small, but I believe it is large, not small. The reason being why I say it is large, everybody is talking about SMR. Since last 5 or maybe a decade long, we are listening about SMR, but nothing has come in ground yet. Throughout the world, nothing has come. We are talking about it only. And we saw Mr. Thierry's presentation also. They are also planning this EDF planning to start the construction only after 2030. A lot of claims are being made about SMR. If we achieve this 2033 target of 5 SMRs, it will be a big achievement. It is not the starting point. Of course, the number is small. It's the starting point. To make these SMRs commercially viable, commercially possible, we need mass production of the self kind of thing. But this is the starting point. So we have to wait for some more time. Now, what is the challenge in meeting this 100 gigawatt? Of course, a lot of challenges are there. Apart from the business environment, what Government of India is already doing, my NITI friend has already discussed, Mr. Manoj has already told how this is making business friendly, the sector is making business friendly. I don't see that is a challenge. That is already being discussed and will be done. The main challenge, I see 3, 4 things. One thing you asked about the capital investment from privates and FDIs. You see 100 gigawatt, in the worst of imagination, if you say about the present cost of about 25 crores per megawatt, you can imagine how much money you need. Of course, we need multiple sources of capital, maybe FDI, maybe private. It is not possible to arrange such a capital, huge capital from the government sources alone. So we have to tap private, maybe FDIs also. The second challenge is the fuel. See, if the world is targeting 1,000 gigawatt, tripling the capacity from where we are now at about 400 gigawatt of generation capacity to 1,000 gigawatt of generation capacity, and India is planning 100 gigawatt. So 1/10 of world's production will be required in India. We have only less than 2% of production. So that is a bigger challenge. So we have to find an alternate source. Maybe we have maybe uranium source may not be sufficient, so we have to plan some more fuels like thorium, which we have a lot of reserve in India. So that also we are trying to how to secure that fuel sources to meet this 100 gigawatt. Third one is the human resource. You need a lot of human resources. This is a knowledge-driven sector. Nuclear is a knowledge-driven sector. So we need a lot of manpower. Capability development is one of our priority area that we are trying. That is one of the challenge. Third is the inputs like land and water. How Mr. Tiwari talked about exclusion zone and all those things. So how much land how much sites, greenfield sites you need in order to meet 100 gigawatt. And at the same time, you need water also. We do not have much of the coastal sites in India. All our coastal sites are thickly populated, and fertile land also. So we'll not be able to get so much of coastal sites. We have to go inland. Once you go inland, then you need lot of water. So about double the amount of water which a thermal power plant needs, maybe 10 times of water what a solar power plant needs. So for that, we are trying to adopt innovative technologies like dry cooling system, adopting air-cooled condensers. Nowhere it has been adopted so far for a nuclear power plant, but we are trying to adopt it so that you reduce the dependence on fresh water. Getting land may be easier than getting water. The last but not the least challenge is the public perception towards nuclear. Now it is changing. Initially it was, maybe negative, but I see a lot of changes in the minds of the general public also. The awareness is being changed, and we are trying to advocate the nuclear energy, acceptability of the nuclear energy, advantages of the nuclear energy in the minds of the public. So these are the challenges we are targeting to meet, taking care of to meet the huge target, and about whether it is a optimistic challenge, 100 gigawatt is optimistic challenge, achievable, not achievable. It's a lot of, it's not very straight question to be answered. Of course it is challenging. Of course it is a very stretch target looking at the past, whatever we have added so far. It's challenging, but I believe it is achievable. By proper planning, proper change in strategy, it is achievable. That's all from my side. Thank you. Any question?
Questions?
Yes.
No, we have to go to lunch, but
Yeah.
there's a question for you and for our friend from NTPC. So we have the same debate about cost in the United States. We think SMRs are for industrial applications first, because what is the cost of outages?
Cost of?
What is the cost of outages? So the LCOE process is designed for residential. When industrial facilities go down, you lose revenues, and in the chemical plant case, you have the cost of bringing the plant back up. That's not discussed in the LCOE analysis. It's a different framework. So I assert that could be where you go first. Possible with private company participation.
Okay. You see, as far as I believe the applicability or the usability of SMR is for energy sector, not the power sector alone. And mostly the other form of energy which the industry needs, like your fertilizer, steel, aluminum, and other food processing industries where heat is directly can be used, maybe HVAC and all those things. Pardon? Yeah. So by that, the LCOE can be controlled, number one, because at that time, using this heat source directly, your efficiency level goes maybe as high as 80, 85%, 90% from the present. If you produce electricity alone, it restricts about 30% or so. If you see the water-cooled SMRs, at best, if you go to sodium-cooled or molten salt, it may go up to 42%. But if you go for trigeneration, both use of electricity as well as heat, process heat, then you may reach up to 80-85%. So thereby the economics of SMR is can be made more commercially attractive, number one. Number two, of course, the mass. The whole utility or whole success of SMR will depend how you are convincing the regulators to reduce these requirements of emergency planning zones, the biggest thing, and the exclusion zone at least. If that is not being addressed, then SMRs is it cannot be made successful. Because if you want to produce electricity with a 1 kilometer exclusion zone, why should not I go for a large reactor? Why should I go for 100 reactors producing maybe multiplied by 100 megawatt. So I should go for, instead of that, I would go for 10 reactors of maybe 1000 megawatt or maybe 1600 megawatt. That will be more economical.
But not as good for heat.
It's not, it is good for heat. Why it is not good for heat? But the larger, only thing is that, yes, you cannot have a process industry very nearer to the reactor. That is the only problem for a large reactor. Otherwise, it is same. It is producing steam. SMR is also producing steam. The same parameters, almost the same parameter. 300 degrees centigrade up, roughly 40 bar pressure. The PSWR reactor is also producing the same. PWR reactor is also producing the same steam. It can be utilized.
Talk to the chemical companies. You get a different answer.
No, the problem, that's why I said, you cannot place a chemical factory nearer to a reactor. That is the problem. If same thing happens with a SMR, again, the same, you will not be able to make it success.
That's not true in the U.S.
That is?
No, in the U.S., the chemical companies are talking about co-location.
For SMRs. Again for...
Only SMR.
Yeah, that's why it depends upon a regulator.
Yeah.
Whether that is being allowed or not, yet to be seen. No regulator in the world has approved these SMRs yet with a maybe zero exclusion zone. It may not be zero exclusion, maybe 100 meters, 200 meters of exclusion zone. Nobody has, this is in the wish list only. And that decides the success of SMR today, I believe.
Yeah. Yeah. So, as Mr. Samal has rightly said that suppose I have to use electricity only, then why SMR? I can put a plant at anywhere in the country, and India has such a massive transmission infrastructure, and our infrastructure is also relatively new as compared to US or Europe. So we have built recently this complete infrastructure. So today if I want to put up a nuclear plant in Odisha and bring power to Madhya Pradesh or Gujarat, it is very easy for me to bring that power. And if I am able to get a better levelized cost of energy with higher capacity nuclear plant, then why I should go with a small modular reactor. So the only thing is, what I personally believe that whatever we are talking of SMR, finally it has to be cost competitive. Cost competitive in the total cost of ownership or levelized cost of energy. If I'll say that my SMR cost in terms of per kilowatt is slightly higher, but still it doesn't require any exclusion zone, it doesn't require any emergency planning zone, still it could be competitive in those terms, because somebody may like to put these SMR within their existing manufacturing industrial unit, and those some transmission cost or some land cost and those type associated costs should be reduced. Having said that, we believe that if we have to use SMR in India, then definitely we have to also think of doing some localization so that we are able to bring down the cost of these SMR to around $200 per kilowatt, so that it is affordable for Indian also.
Okay, thank you very much. Yes, wonderful.
I had a question, if that's feasible.
All right. Yeah, I believe as a conclusion of this session, we discussed a lot of important points. I think the choice of technology is very important here. I think there are so many technologies that are around. If we are going to use the nuclear for industrial applications, I think there are technologies that exist. They can coexist with the current production facilities. I think that's the way to go. And if it's only for electricity, I think the issues remain the same. So from my perspective, there is a book out there, it's called No Nuclear is Hot, which can take care of all industrial applications providing high temperature heat, which is the requirement for industries. I think that's the way to go. New nuclear is hot. So this is real. So it's written by Robert Hargreaves. It's available from Amazon. New nuclear is hot. So we mostly discussed here with LWRs that are low temperature, but the new nuclear SMRs could be very high temperature, And I think they can be co-located at the industries because their footprint is very small. I don't believe there is any exclusion zones required, of course. We have to convince the regulators, but that shouldn't be that difficult, knowing these technologies. Thank you very much.
Thank you, sir. Thank you. Thank you, all speakers, for sharing your insightful thoughts and valuable contributions on nuclear resilience and the role of SMR for the net zero power systems. I would request Ms. Reena ma'am to facilitate our speakers with token of mementos. Please come, ma'am. Starting with Mr. Ganapati Myneni. Mr. Andrew Paterson. Mr. Timothy L. Head. Mr. Everett Redmond. Mr. Kailash Mittal. Mr. Thierry Advocat. Mr. C.P. Tiwari. Mr. Arnada Prasad Samal. Thank you, ma'am. I would request all speakers to come forward for group photo.